Hi guys, today's topic is how to analyze time series data. So basically time series data means the data which changes with respect to the time. Like you have a data which is changing hourly, daily, weekly or monthly, quarterly, annually. So this kind of data is called as time series data. So I can say the example for this time series data is like stock price, weather data and gold price. So this kind of data is an example of time series data. So it's very important how to analyze such kind of data. So we can use pandas to load the data, and then we can see some classical methods how to analyze time series data, and then I will see how to build a time series model using ARIMA. So first of all, how to import time series data. So pandas provides the facility. So we can first importing pandas here, and also importing Matplotlib for data visualization. And this plot predict is the function which is used to plot the time series values. So these are imported, and then I'm loading the data. So here our data set is we have some 8 passengers data which has been downloaded from Kaggle. So I kept this data in my data folder, and loading the data and creating a data frame. So data equals to pd dot read CSV. So we are reading the CSV file, then displaying the header part of the data. So head means by default it displays first 5 rows. So you can see there are two columns. The first column is month, and the next column is number of passengers. And in the month 1 1949, the number of passengers were 112. And then you can see the increase in month 2, again increase. So we can see the passengers have been increased from 1949 month 1. Next I'm checking the data type. So data dot d types, which gives us the data type. As you can see, there are two columns. The first column's data type is object. Object type means string type of data is considered here. And the second column, the number of passengers, the data type of this is integer 64-bit. But basically the month column should be time series. So that is why. So we are loading the data set again, creating a data frame, and we are adding this parameters. Past dates is equals to true, means date is passed, and we make the month column as index. So this is the argument, index call equals to month, and then displaying the header part of the data. Now you can see this is the first month. Of course date is added here 111, but actually it is referring the month. So month and then year. So now it is transformed into time series data. We can see the index. So data dot index. So here we have the data from 1949 month 1 to 1960 month 12. So the length of the data is, you can see, totally 144 terms, means 144 months. And then I'm subsetting the data. So TS is equals to data of passengers, then displaying the head, and the parameter over here is 10, means first 10 months, and this is the data. And we can do indexing and time series slicing here. So specifying the index, that is 1949 month 1 day 1, what is uh, the number of passengers, which is equals to 112. Similarly, you can also use a date time imported from date time module, and then specifying the date time value by using the date time function, year, month, day. Then you'll be getting the same value, 112. Then here we are using slicing, month 1 to month 5. So we'll be getting 5 months data, month 1 to month 5. Then this is also slicing, but starting is not mentioned. So by default it starts from the index 0, means first month, up to month 5. So the same output. If you give the year, then it is going to display totally 12 months, month 1 to month 12. So once we have loaded the data, then the important question is, how do you check the stationarity of the time series data? So we can have a plot of TS. So PLT dot plot of TS. You can see this data is uh, this data is having a positive trend, means as the number of months are increased, the number of passengers also have been increased. So there is a positive trend. Next, importantly, we can check the stationarity of the data in two ways. The first way is plotting the rolling statistics, means how the values are changing. That means moving average and importantly moving variance. So by using these two, you can see the data is no stationary or non-stationary. Or else you can also have the another method, that is you can go for a decay Fuller test. So this decay Fuller test is one of the method to check the stationarity. It gives you some parameters, and based on the parameters we can say the data is stationary or not. So we are getting the mean. So window equals to 12, means first for 12 months having a mean here, and then STD means standard deviations. So these two are retrieved and then they are stored into the variable rolling mean and rolling standard deviation. And this is the class which is imported from the module statsModule.tsa.stats tool, and we are creating a method here or test stationarity, which is taking three parameters: time series means the actual data, then moving average and moving standard deviation. And we are first plotting a graph here, so specifying the graph size 10 by 4 and plotting the actual values, time series values. The color used for this is blue, and the label for this is original. And we're also plotting a rolling mean, which is represented by a red color. Then standard deviation is plotted by using black color, and you can see the labels here. And also we are adding a legend, location equals to best means, which is displayed at the best free space. And this is going to be titled rolling mean and standard deviation, then plt dot show. So you can have a graph on which you can see the original data, moving average and standard deviation. Below that we are also printing the decay Fuller test values. So this is going to be displayed exactly. Then using the function add Fuller time series, and auto lag is AIC, means AKK information criteria, and creating a time series. So here creating a Pandas series here, PD dot series of basically this test give us four values, so 0 to 4 slicing indices of that, and these are the labels: test statistics, p value, the number of lags used, and the number of observations used in the analysis. And as there are four values to be displayed, so we are using a for loop here for key comma value in df test of 4 of items. We are just printing the values and also printing the df output. And so this is definition, so we are calling the above method over here by passing three parameters: ts, rolling mean and rolling standard deviation. So as you can see, the blue color one is the original value, and then mean is represented by using red color, and this black line is the standard deviation. And these lines are not straight, so it means the data is not non-stationary. So you can see the results of the decay Fuller test. The test statistic value 0.81, and as per statistics, this value should be less than, test statistics value should be less than the criticality value. So the number of observations used over here is this 130, and then you can see 1% criticality is minus 3.48, and 5% criticality is minus 2.88, and 10% criticality is minus 2.47. So we can just manually check whether the test statistics value is it less than the 1%, 5% or 10% criticality. So at first we are checking with 1% criticality, so this is false. Then checking with 5%, so this is also false, means not even 5% of the data is stationary. Now the question is, how do you make the time series data stationary? So time series data means which is having two things. One is a trend. Trend means varying mean over the time. So mean varies. And seasonality. Seasonality means variation in specific time frame. For example, trend could be positive, means if x value increases, then y value also increases. Sometimes it could be decrease, negative trend. And as we have seen in the graph, so we have positive trend. The number of passengers have been increased. And seasonality means that data value increases over a particular time. For example, um, cars are purchased during some festive seasons, right? Or when the value is decreased or increased. So most of the time, people prefer to purchase cars during the festival season. And another example I could take is, for example, woolen jackets are purchased or during the winter season only. That means of certain kind of products are having more sales during a particular period. For example, during the December month, and on the on the occasion of this no, Christmas, there are products which are sold. So this kind of data is called as seasonal time series data. So the next important thing is, how do you make the time series data stationary? So first we need to make the data stationary so that the model can give us the correct predictions. So the first challenging task is how to make the data stationary. So the first classical method is you can estimate and eliminate trend. So here I am performing a log transformation, importing NumPy and then np.log transformation on the time series data, and then we are plotting. So you can see the graph over here. Still there is a seasonality. So data has not become stationary. Then we can also opt other methods like doing some aggregations, means taking average for a particular team for a particular time period, like monthly, weekly averages. And smoothing means taking a rolling average and fitting data to some regression models. So these are some classical methods. So if you go for first one, that is a moving average. So on log transform data, we are now performing mean for window size 12. Similarly, applying standard deviation, then checking the stationarity. So you can see, let's check the decay Fuller's test here. So these lines are not straight, right? So you can see the test statistics value, which is minus 1.71. And is it less than 1% criticality or 5% or 10%? So we are checking here. So the condition is false, the result is false. With 5% criticality also, we got the result as false, means data has not become even stationary. Now next what we can do is we can do the differentiation. So moving average is subtracted from log transform data and displaying the first 12 months. So when you do that, you see these values have become NaN, means missing values. So from month 1 to month 11. Next we can remove this no, we can remove missing values. So from DS log moving average differentiation, drop NA means dropping the missing values, in place is equals to true, and then displaying the header part of the data. Now we have got the values from 1949 month 12, remaining have been removed, and then on this data, on this log transform and moving average differentiation, we are applying again mean and standard deviation, and then checking the stationarity. So you can see how these mean and standard deviations are plotted on the original data. So as you can see, still the series is non-stationary. Now we can check the condition, whether the test statistic value minus 3.116, is it less than 1% criticality or 5% or 10%. So if we check with 1% criticality, the result is false. Even with 5% criticality, it is with 5% criticality it is true, means 95%, okay, confidence that this series is stationary. Understood? So 95% the series have become stationary. So remaining 5% is non-stationary. So in this case, the drawback over here is if you don't specify the time period properly, then your result is not going to be accurate. Your model is not going to be accurate. So the drawback is time frame here. Then we can take we can consider the another method, that is exponential weighted moving average. So this is the method on log transform data. You're applying EWM, means exponential weighted moving average for the window size 12, then taking the mean, then also calculating the mean and standard deviation on the exponential weighted moving average, and then taking the difference, and then checking the stationarity. So when you do that, the lines have been become this original data and standard deviations are quite on the same axis or same plane. Now we can check the stationarity. So minus 3.60, is it less than 1% criticality? So let's check the condition. So this is true, means data has become 99% stationary. Okay, data has become 99% stationary. So we can conclude the test statistic is smaller than 1% criticality. So 99% the series has become stationary. So these are the classical methods how you make the data stationary. And we can also have these methods like so taking the difference and decomposition. So basically time series data means it is having trend and seasonality. So if you remove trend and seasonality, then the data becomes stationary. So taking the differentiation, so TS log shifting, so shifting the values and then subtracting that from the TS log transform data and then plotting the data. So as you see, the peak values have been removed, and next dropping the missing values, and then on this data taking the moving average for window size 12, and then window size 12 standard deviation, then checking the stationarity. So now let's check the stationarity. Minus 2.71, is that less than 1% criticality? So it is false. Is it less than 5% criticality? So it is false. How about with 10%? With 10% it is true, means 90% the series has become stationary. And we can also go for decomposition. So this decomposition means you can first plot the trend and seasonality, and after that you can remove the trend and seasonality, then the data becomes stationary. So from PyLab, importing the RC parameters to specify the figure size, and we are using statsModel.api. This is alias SM's stats model, and this is an important function, statsModel.tsa.seasonal decomposition applied on log transform data. The model is additive, means the data is added, and then plotting a graph here. So by plotting decomposition, you can see what kind of trend you have and is there a seasonality. So the first figure, this is no original data, so there is a positive trend, and we are also plotting a separating trend. So if you look at this second graph, so there is a positive trend, means as the number of months have been increased, then the passengers also been increased, and seasonality is also there. Okay, so decomposition means separating a trend and seasonality. So as you can see, there is a seasonality ups and down, and you are also plotting the residuals. So you can see the points are not on the lines, and these dots are called as residuals, means errors. So then what we can do is you can remove these trend and seasonality. So getting the residuals into the variable TS log transform decompose, then dropping the missing values, then again calculating the mean and standard deviation, then checking the stationarity. So if you check the stationarity, so you can see the test statistic value minus 6.33. Is it less than 1%? True. Is this less than 5% true? 10% also true, means 99% the series has become stationary. So this is also the classical method. Then instead of using these classical methods, you can also go for the model, that is ARIMA, which stands for autoregressive integrated moving average. So basically this model is considered as the composition of regression, integration, and then moving average. And if you properly specify the values of PDQ, which are the elements of ARIMA model, then your series is going to be stationary. So now we need to understand what is the meaning of P, what is the meaning of D, what is the meaning of Q. So P means number of autoregressive terms. Number of autoregressive terms. For example, if you take the value as if you take P value as 5, then the predictors are no, represented as x of t is going to be x of t minus 1, next t minus 2, next t minus 3, up to t minus 5. So and then Q means, which represents the number of moving average. So moving average terms. So you can take Q equals to 5, then predictors of x2 equals to e of t minus 1, t minus 2, up to t minus 5. And D means differentiation. So what is the differentiated value? So most of the time it is taken as 1. The value for D is very small, like you can take 0 or you can take 1. So it means the number of terms to be differentiated. And for this ARIMA model, it is very important to specify the appropriate values for PDQ, then the model is going to be accurate. So the question is how to determine the value for P and Q. D value we can take 0 or 1. So this can be done by using two graphs. The first graph is autocorrelation function, in the short form ACF, and the second graph is partial autocorrelation function, PACF. So by plotting these two graphs and checking the values, they can see what is the value for P and what is the value for D. So importing these two functions ACF and PACF from statsmodel.tsa.stats tool, then we are using the function on the TS log transform data, the number of logs equals 20, and also getting the PACF. So this gives us the ACF and PACF values, and then here by using Matplotlib we are plotting the values ACF and PACF. So the first graph is autocorrelation graph and the second one is partial autocorrelation graph. So from these two graphs you can determine the value for P and you can determine the value for Q. So P means the lag values where PACF chart, this one, the second one, PACF chart crosses the upper confidence value, where it is crossing the upper confidence value. So we can see approximately 2 here. It is crossing the upper confidence value approximately 2. And from ACF graph you can determine the value for Q. So here also the same same rule, where this ACF value is crossing the upper confidence value. So from here also we can consider 2. So we have determined what is the value for P, which is 2. We have also determined the value for Q, which is 2. So now you know what is P value, what is Q value, and then D value you can give 0 if you have already performed differentiation, or you can have D value as 1. So ARIMA, as I mentioned, is a combination of three things. The first one is autoregression, the second is integration, and third one is MA. So we are building three models here. First is AR model, and here I'm importing warnings and filtering the warnings. So for this, these lines are required. And look at this, ARIMA is imported from the module statsmodel.tsa.arima.model. So once the model is imported, so creating object to that model, so model equals to ARIMA. So this is the data TS log transform differentiation. we have already done the differentiation, so that's why D value is 0. So P value we are taking 2, and Q value should not be taken in case of AR model. So in case of AR model, uh, Q value should be 0. In case of MEA model, P value should be 0. So that is the difference between AR and MEA. So the first model is AR, so giving the order 2, P value is 2, D value is 0 because we have already done the differentiation, and Q value is 0. This is frequency based on the month. Even you can remove this also. Then we are plotting the original values and then differentiated values, and here we are calculating the RSS, residual sum of square values, which is now printed on the figure. So result ARIMA dot fitted values minus the actual data square, which is nothing but RSS. So we are plotting the RSS value, and you can see the original data, which is represented with the blue color line, and then the red color line representing the data values fitted to the model. So these are the fitted values, red color line. So the number of peak values, so peak values have been reduced, and you can see RSS value is 1.50. Now next we can build another model, MEA, moving average model. So in case of MEA, P value should be 0, and giving D value as 0 here because we have already done the differentiation, and then Q value we are giving it as 2. You can remove this also, no, it doesn't affect, and then getting the graph. Now you see RSS value has been reduced. When you compare AR and MEA model, with AR model RSS value is 1.50, and with MEA model RSS value is reduced to 1.47. So this is more red color line is more fitted and accurate. And as I mentioned, ARIMA is a combination of AR, MEA, and then I. So this is the combined model, and we can say this is the ARIMA model. So specifying the order value, P value 2, differentiation is 0, Q is 2. So when all these P, D, Q are specified, then it is ARIMA model. So getting the RSS value, we got it as 1.21. 1.21. Now we can just compare these three models. So in case of RSS, the combined model has less value, 1.21. So this is the better model. So like this ARIMA model is developed, and now getting the summary of the model. So model summary is this. You can see the AIC value, which is negative here, and then you can also check out the residuals. You can also check out the residuals. So this is the combined model which gives some better results. Even we have applied different types of operations on the original data, like we have made a log transformation, then differentiation and all. So we have to get the original data. So in order to get the original data, what we are doing is getting a Pandas series here. So result ARIMA dot fitted values, making a copy of that, and then displaying the values. So what are the actual values fitted to the ARIMA model? So this is the these are the values, but these are not the actual values, right? So we have started the data from you can see that the month is 2, but actually we have starting from month 1. So what we need to do is, next is very important to take the cumulative sum. So prediction ARIMA differentiation dot apply cumulative sum function, then displaying the data. So these are the cumulated values. Next we are again getting a series here, PD dot series of TS log transform of 0 is added, then getting the index of that, and then adding that to the this above series, and then displaying the header part of the data. Now month 1 is also added. So here we are starting from 2, so month 1 is added. Next now we can make a plot here. We can compare the plot here. So taking a now exponentiation because to get the original value on this prediction SARIMA log transform, then plotting the actual values and also what the model has predicted, and getting the RMS value. So the RMS value is quite reduced, mean square error value is quite higher, 135.5235. You can say these are the original values, and this one, this what the data fitted to the model. So the number of peak values have been reduced, and this one is somewhat stationary. This is not that much accurate, but this is the ARIMA model's outcome. So this is the how the time series data is analyzed and how do you build a model. We can also go for getting the auto ARIMA model. So with this model or with this approach, the drawback is how do you determine accurately the value of PDQ. So giving the proper value for PDQ is very important. So in order to get the proper value, so we have auto ARIMA model. So that auto ARIMA model automatically gives us the approximated, means optimized value for PDQ, and if you substitute those values, then your model is going to be accurate, or it is going to be a very stationary model, and that will forecast your future predictions. So let us see that. So getting the auto ARIMA model. Okay, plotting a auto ARIMA model. So I'm using the same data set here. Okay, using the same data set, and then how to build a auto ARIMA model. So in order to get the auto ARIMA model, you have to install the library. The library is this. So you have to install the library PMD ARIMA. Okay, PMD ARIMA. So if you don't have it, you can install it by using pip install PMD ARIMA. And one more important point to be noted is we have two types of ARIMA model. So first one is normal ARIMA, so which is non-seasonal, means if there is no seasonality, then you can use this ARIMA. And another model is SARIMA model, means seasonal ARIMA. If there is a seasonality in the data set, then that is called as SARIMA, means ARIMA model with seasonality. So here I'm importing Pandas, Matplotlib, and then once you have installed this PMD ARIMA, you can import it, and the alias is PM, and you can also ignore warnings. And after that, I'm loading the data set again, and the same approach. Index column is month, pass date equals to true, then displaying the header part of the data. Now this is our data frame. Month column is index, and the number of passengers is the column. Then we are importing seasonal decomposition. We are doing the decomposition of the decomposition on data, and this is the important function, seasonal decompose, and this is the column which is fitted, and then model is multiplicative, or you can also take additive. So the data is taken, and then for more information you can also take help on this particular function or the parameters, and or you can just know the meaning of these parameters. And then just having a plot on the plot of the original data. So when you see the plot, you can see this is the actual data, and there is a positive trend, and there is also seasonality, and there is a residuals, right? So this is plotted 2 times. And then so this is the very important. So importing auto ARIMA from PMD ARIMA, and then auto ARIMA, creating an object to this, and then this is the actual column which is fitted to the model, and start P equals to 1. So start P equals to means what is the starting P value, then maximum P value you can determine. So 1, start P value is 1, means in the range of 1 to 3. Also taking the range for Q. 1 start is Q, start Q is 1, and max Q is 3. Window size we are giving 12 months. Then the start P equals to 0, seasonality. So this data as already it is having the seasonality. So seasonal equals to true, and then this D value is none, capital D is 1, trace equals to true, and then error action equals to ignore, means we don't want to know the if an order doesn't work, so we just ignore it, then warnings are suppressed and stepwise equals to true, then this gives the summary of the model. So you see the data is being fitted to the model, and you can see the lower value for AIC, lower value for AIC, and also it gives the um, optimal value. What is the seasonal value? You can see the best model. The best model is this ARIMA. This is the order to be maintained 0, 1, 1, and this is the seasonal order 2, 1, 0, 12, and this one 0, 1, 0, 0, 1, 0. Where is this 0, 0, 1, 1, 0, 1, 1, and then 2, 1, 0. Okay, 0, 1, 1, 2, 1, 0, which has a lower value. So where 0, 1, 1, 2, 1, 0, this one 0, 1, 1, 2, 1, 0, this one is lower. So 0, 1, 1, 2, 1, 0 for this. So it is suggesting this is a less value, but we also have 0, 1, 1, 1, 1, 1, 12, so 1, 0, 2, 0.327. So not this one. So this is the lowest value, getting 0, 1, 1, 2, 1, 0, 12. So this is the lowest value, and it is, you can see it is also giving the summary here. SARIMAX seasonal ARIMA, and AIC minimum AIC value is 1019.178, means this one itself. So this model has suggested what is the best model. So if you take these parameters, then your model is going to be accurate. So next, you can also take help on this model, this function. What are these? What are the meaning of all these? Start P, start Q. What is capital D? So capital D means here. Small d means this is the integer value, which is also optional, which indicates the first order differentiation. And capital D, capital means the order of seasonal differentiation. This is the seasonal differentiation, like this. With seasonality you have to maintain the capital value. With there is no seasonality, these lower values, lowercase values P, Q, D are applied. So you can have just look on that. And then I'm checking the length of airline. So totally we have 144 instances, means terms. Next, what I'm doing is getting the splitting data here. So train equals to airline dot airline of starting from 0 by default to up to length minus 12, means we want to use the last 12 months for testing. So minus 12, and then test equals to airline dot I location length of the training data minus 12. So means we are setting last 1 year or last 12 months for testing. So data is separated into training and testing, then importing SARIMAX from this module, and then building a SARIMAX model here. We are using the same order. So that is 0, 1, 1, what it has been suggested over here. So the same, this one. So we are using this, and that is the order, seasonality is this, and then fitting the data and then getting the summary of this. So on this data, the minimum AIC value is 901.659. Then we can, I'm just checking the length, so 132 after subtracting the last 12 months. Then again calculating the start is length of train, end is length of train plus length of test minus 1, because range is always minus 1. And then making the prediction. So by using the model result dot predict, starting from start to end, type is levels, and renaming the particular values. That means what the model has, what the model predict. So for that the label is predictions, and then making a plot, prediction dot plot, legends are added, also applying the test values on the graph. So when you do this, the predictions, the blue one, and the actual values are orange one. So the blue one, orange ones are almost closer, right? So these are closer. And then we can evaluate this model by using the metrics like mean square error I hope you guys know what is mean square error and what is a reduced mean square error. So these two metrics are imported from scikit-learn.metrics and also statsmodel.tools.evaluation measures, and then getting the RMSE value here, RMSE on the test data, comparing what the model has predicted and what are the actual values. So if there is a difference between what the model predicted and what is the actual value, then that is going to be an error. So RMS value is 18.38. As you know, as per statistics, the error means always we expect it is closer to the 0. So we cannot always build a 100% correct model here. So the RMSE value is 18.38, and also getting the value for MSE, mean squared error, that is 337.85. So once you have built a model, you can forecast. Forecast means you can make the predictions for future months. So using our model again, so model equals to SARIMA here. This is the actual data, maintaining the same order, then fitting the data, then making the prediction for start equals to length of this plus end. So end to the end we are adding 3 comma 3 multiplied by 12, means we are making the forecasting for next 3 years. Understand? For next 3 years, and renaming that as forecast, and then having a plot on actual data, airline of passengers, plotting the values. This is a figure size, legends are added, then forecasting is also plotted on the graph. So after running this cell, you can see these are the actual values. So the blue color line is the original data, and this forecasting is represented by orange color line. So this is forecasting for next 3 years. And as per the data, we have the year, right? The last year is 1960, month 12, and you see it has made the prediction for next 3 years. So 60 plus, so 1963, month 12. So this is the forecasting for next 3 years. So like